Hello, I'm NASA Curriculum Specialist Rochelle Oblak. In this video, I will discuss the What Makes a World Habitable lesson located within the Planetology unit. In this lesson, students explore the characteristics of planets or moons that make them hospitable to life. Students use pre-printed cards called habitability cards that contain facts on the planets and select moons in the solar system. Included in the lesson is a highly recommended math extension. The activity is called What Makes a World Habitable? It is activity number 3 in the Astrobiology in Your Classroom Educator Guide, Life on Earth and Elsewhere, located on page 23.
Teachers need to prepare the cards for the class ahead of time. Print the habitability cards on heavy cardstock paper. Print the image of the plant or moon on the front and the details about the planet or moon on the back. I would recommend that you laminate the cards for future use prior to starting class. Teachers also need to print the student worksheet to accompany the habitability cards. Also included in the lesson is a key discussing the temperature, water, atmosphere, and more about the planets or moons that may or may not harbor life. You can hand these out to students or create a large classroom poster of the requirements for students to reference when completing the activity.
Begin with the class discussion. Ask students, what makes a planet or moon a good home for living things? Record all answers in a central location. Also, review the requirements for life such as food, water, protection from radiation, suitable temperatures, and so on.
Students work to sort the habitability cards based on the requirements for life as they fill in their worksheet. Once they complete this portion of the activity, I highly recommend you complete the math extension activity. While sorting the cards, students learn that the distance from the sun affects the habitability of a planet or moon. At certain distances, sunlight is too dim to be a viable energy source. You can demonstrate this simply by holding a flashlight or a light source at a distance. Light closer up, light further away. As it gets further away, the light is more dispersed. It's the same idea when you sit by a campfire for warmth, you wouldn't want to sit too far away. What students may not realize is that the distance to a planet or a moon and the energy from the sun are mathematically predictable. This is the inverse square law and is easily demonstrated using an overhead projector. I have an overhead projector here. In the classroom, you will need to measure a distance from a wall or a board of 1 meter. If you don't have a 1 meter space, you can't alter the size. So I'm going to bring mine in here very close so that you can see it. And assuming that I have my projector placed at 1 meter away from the board or wall, I am now going to trace the illuminated portion, making a square. You'll repeat this procedure 2 more times, each time moving the projector back twice the original length. So you will go to 2 meters, 4 meters, and so on. And you can repeat this as much room as you have. When you are finished, as an example, you now have the data that you could use to calculate the inverse square law. You have the distance to the projector, and you then measure the side of your square. Students can then graph the data. Next, introduce the math of the inverse square law. I have my 3 distances labeled here. In the inverse square law equation, I have 1 divided by the first distance, which is 1. Recall that we placed the projector the first time at 1 meter. 1 divided by 1 squared is equal to 1. This is our reference intensity. For distance 2, I have 1 divided by the distance, which was 2 meters the second time we moved the projector out, squared, which is equal to 1/4. Notice here that the distance only increased by 1 factor, whereas the light intensity is now 1/4 of the original reference intensity. You can add as many times out as you would like, as many distances, and have students predict what would the next intensity be. Next, students need to use the light intensity of Earth, which is a known quantity, 1,370 watts per meter squared. Again, this is our reference intensity. You will take that number and complete an example for students. We're going to do mercury. Mercury is 0.39 AU, or astronomical units, from the sun. Recall that 1 astronomical unit is actually the average distance from the Earth to the sun of 93 million miles. Substitute the information into the equation. 1 divided by 0.39 AU is equal to 6.575, or roughly 657.5%. That means that the light intensity on Mercury is 6.5 times the intensity of light to our reference point, which is Earth. You can use this information then to complete another calculation. You take the original calculation that you made on your particular planet, 6.575 times 1,370 watts per meter squared, and you get an intensity of light reaching Mercury of 9,008 watts per meter squared. Students then repeat the calculations based on this example, and then they complete a table in their lab notebook.
Many NASA resources allow you to extend the learning for this lesson. For instance, you can look up recent planet discoveries at the Planet Quest site from the Jet Propulsion Laboratory. Locate a planet in another solar system, calculate the amount of light reaching the planet, and then make inferences on the habitability of that planet. Teachers may also want to use the available multimedia resources on the site to extend or even introduce the topic of habitability and the search for life on other worlds. On the Planet Quest site from NASA's Jet Propulsion Laboratory, you can explore recent planet discoveries. One section to investigate is the multimedia page. Here you will find overviews, interactive multimedia, and more for student exploration and extensions. For extending the information on the inverse square law, go to the New World Atlas. Select all extrasolar planets for a table of the discoveries made to date. Select any planet, such as 47 Ursa Majoris b. An interactive window pops up. Locate the average distance from the star. The distances are listed in astronomical units. For simplicity, it is best to look for planets that have stars similar to our Sun. Use the chart to browse the stars and look for those with characteristics similar to our Sun. You can also use the interactive atlas. For NASA Summer of Innovation, I'm Rochelle Oblack. Thank you for joining me as we explore together.